كلمني على ده.
No, I will ask him. We agree. He told me he's gonna give it to me, and then I spread it, and then I won't give it to any one of you. It's very straightforward, you know. If you need to take it, you have to come and take it by your hand, you know, by force. الايه؟ الستيل زي ما هو موجود بره من ساعه ما اتحط، بس راب بالبلاستيك شيتس. ومن ساعتها ما اتشال، الكفر ما اتشالش من عليه، يعني هو من ساعه ما جه احنا غطيناه كويس جدا وحطينا عليه بقى اللي هي عارف التراب اللي هي الطار دي اللي هي بتاعت البلاستيك دي كتير كبيره، بس هي لونها مش شفاف، هي خضراء وزرقاء سيكون يعني. وحطينا كونكريت بيمز وكيوبس، فمن ساعتها ما اتعتعش، ما اعتقدش ان هو حالته هتكون سائد يعني. هو بره اللاب، بس هي المشكله الكبيره هتبقى ازاي تشكل، او انت عارف هو 24 فوت، فده اصلا ولا هيروح ماشين شوب ولا يعني، لازم اي حاجه تتقطع مكانه. انا عايز نشتري بقى واحد اللي هو عندنا الكاتر درين، بس الكاتر اللي هي الاسطوانه الديسك ده بيطلع شرار. في واحد تاني بقى جبت واحد لجاري عنده، ممكن استلفه منه، قال لي لو احتجت تستلفه استلفه. بتاع كده هاندي عباره عن بليت، بس البليت فيري فاين بليت، فانت بتمشي في البار كده ما بتطلعش شرار يعني. قصيت بيه البري ستريسنج بار عندي كده، هو قصدي طبعا بس يعني بدون شرار. فده التاني طبعا هيت عالي جدا وانت بتقطع التاني والشراره وبتاع، فده احسن بصراحه، وخصوصا لو هنقطع كتير يبقى يفضل ان احنا نجيبه. هو قال لي ساعتها يعني، قال لي خده ولو حبيت تستخدمه خده، فممكن ساعتها بقى استلفه منه، او لو احب وممكن نجيب واحد. ما اعتقدش ان هو يبقى غالي.
All right. So again, this is my part now. I'm 10 minutes late. We'll talk about liquefaction and assessment and retrofit. I want to maybe talk about a few case studies, actual projects that we've done, and some of the lessons that we've learned. My thought is that we go for a couple of hours, so maybe 3 o'clock-ish, 3:05, 3:10, wrap this up. And then if I could have your kind attention for 10 minutes, I have a little presentation about my company. Because I'm here, I might as well tell you the fun kind of work we do so that after you graduate, you can maybe reach out to us. So if you don't mind sticking around for maybe 5-10 minutes afterwards, I'll tell you about the different streams, the different offices, the different kind of fun work we do. I'd like to share that with you guys.
I will interrupt you maybe around 3:15.
Yeah.
We will take some photos and do
For
some
sure.
certification.
Yes.
And then you can.
And then, so once we finish, we do that.
I also have a meeting at 3 o'clock.
Okay.
So I'll head out at 3.
Yeah.
And then you continue and finish. And
you'll come back by 3:15? Is that what you're saying?
Yeah, like.
Yeah.
Around 4 we will meet again.
Yeah, yes, that you and I will do that. Okay. So we want to talk a little bit about liquefaction analysis and associated design philosophy and some assessment and retrofits. I'm not going to go through these miscellaneous topics. You can read about those in the code. They're not very important for this setting. These are simpler things that I talk about in my other course that goes for 12 weeks kind of thing. So just for completeness, they're there. But I'll give you the PDF, as I've already said, and you can have a look. Maybe I'll talk about this issue, which is a little bit important. We did the retrofit of the McDonald-Cartier Bridge when I was with one of my previous companies. I want to talk about that case study, and then the Evergreen Line design that I was involved with for several years, and it was quite a challenging and satisfying project. I really liked working on it. So, fluids don't have any kind of shear strength, so they just flow. The solids, on the other hand, stay put together because they've got some shear strength. So one section can't just move past the other section. What happens with soil, and especially saturated sands, is when they get saturated, the pore water pressure develops. So any soil, when you put a building or bridge on it, it's got an effective stress on it, and that gives the shear strength that keeps the things interlocked together. Now, if there is water there, the water has a pore water pressure which acts upwards. That's opposite to gravity. And then along comes an earthquake and starts to shake it sideways and up and down. And what that does is it creates an increase in the pore water pressure. The pore water pressure increases. So now the effective stress on the soil is decreasing. And as the effective stress on the soil is decreasing, the shear capacity is decreasing. Until such time, the pore water pressure has come to a level that with the shaking, you have lost enough strength. And because it's putting shear stresses into your soil, the soil liquefies. It just flows like a liquid, hence the word liquefaction. The result is excessive vertical and or lateral displacement. It doesn't happen in clays. Clays usually go through what we call cyclic, not degradation, cyclical softening. Okay, so it's similar, but it's not quite as drastic as sands. So if you have flat ground and you get liquefaction, what's usually going to happen is the soil is going to settle, okay, and it's going to lose the shear strength, it's going to settle, and it's going to affect your structure, it's going to settle. So if you have spread footings, imagine if the soil underneath it settles by a foot, how you've poured your structure down by a foot, and it may not be able to take that. If you have piles, the piles might plunge. If they're founded in a liquefiable zone, the piles will plunge, and the same effect will happen. If you have something different, if your topography is a little bit different, you've got something like that. Let's say you've got a bridge sitting here. And here's the apartment, perhaps. What am I drawing? Something to that effect. Now when liquefaction occurs, and this wedge of soil that's sitting up here loses its shear strength, it doesn't just have a tendency to move down, it also has a tendency to move laterally. And all of this soil, it can slump. So this can move, and also the soil that's here is going to want to flow against these piles or columns. So not only is your structure feeling a loss of vertical capacity in the soil, it's also being acted upon by what we call a kinematic load, which is the load of the soil as it acts against the piles or your footings. And we've had lots of issues in the past with this. We've had lots of failures. And there's one example of a Japanese bridge. There's a photograph, and it's all simply supported spans, and the piers have moved and the spans have fallen down because the seat lengths were not generous. In the Evergreen line, as I'll describe a little bit later, we had a thick crust of soil sitting at the top, which is non-liquefiable. And then we had all this soil underneath, which was liquefiable. So imagine if your soil is very soft and it flows against your pile. It's a bit of an issue, but it's not that big of an issue because it's not very stiff. This is going to flow, it's going to put some load on your pile, it's going to flow around it. So your structure may be able to take it. But if this soil is liquefying, and this crust, which is non-liquefiable, it's very hard, it's just going to want to move as a rigid body. So now it's going to put a lot of passive pressure on your piles. It's not just something that's just flowing around it, it's actively engaging. And it can't stop because all this soil underneath it is moving and it's attached to it. That was a big issue in the Evergreen line for us. We were seeing movements of a meter plus. And the areas where it was just flowing without the crust on top, the design was challenging, but not that challenging. Where we had 500-600 mils of movement here with the crust sitting on top, it was very difficult to make things work. I'll talk about it when we get there. But those are some of the issues that can happen. You can have plunging, you go down, now your superstructure has to accommodate that. If it's continuous, you may still create a lot of distress in your girders and your deck. If it's simply supported and the pier tilts, you might have the span fall off. Yes?
How do you know in advance? I mean, from the soil properties, we know that this would be liquefied soil or not liquefied soil?
That's a good question. I don't. There's a geotechnical report that tells me that we're dealing with soils that are liquefiable.
So during design time, you know that it could be.
Yes. So beforehand, we know what the soil conditions are like, and then the structural solution has to somehow account for that, right? So we collaborate very closely, especially in the Fraser River Delta in the Metro Vancouver area, where this is a huge problem everywhere. I keep hearing that Richmond is going to get hit really hard because it's a man-made island, basically. It's going to be an issue. But I've been involved with lots of bridge design in the Lower Mainland. This is almost ubiquitously present. It's everywhere. Okay, so the phenomenon is saturated sandy silts and silty sands. what we like to do is have a continuous structure in this case, because then if everything is tied together, hopefully everything can move together. Not always. I'll give you an example when we go to the evergreen line, but that's generally the idea that we want to do. Now, another factor that makes things difficult is differential liquefaction. And again, on the evergreen line, it's like we almost dealt with every problem that you can imagine with evergreen line with liquefaction. I had one structure about 18 spans or 15 spans long, and the one abutment basically saw no liquefaction. And the first pier, the second pier, let's move back from the second pier. The second pier was moving about 1 meter transversely. And the first pier was moving about 0.6 meters transversely. And then everything beyond the second pier was moving about 1 meter. So my deformation profile was doing something like this. So if my bridge were here, it was going to be forced to move like that. Now you can imagine if I have a deformation profile like that, at least everything is moving or trying to go together. But when I have this, a real hard point, somewhat of a harder point, and a real weak point, I'm going to crank a lot of differential movement, lots of concentrated load into these areas. It was quite challenging for us to deal with. So what does the code say? Here's the liquefaction philosophy for the design. So the first thing is, if you're in liquefiable soils, do not go with spread footings. Not a good idea. They're going to sink. So you have to have piles whenever there is liquefaction. Unless you can do ground mitigation, you can mitigate the soil to get rid of your liquefaction. And anytime I've talked to a geotechnical engineer, and I've talked to lots of them in my lifetime, they tell me that complete elimination of liquefaction is pretty much impossible. You'll always have some movement. And that's fine if you're going to, maybe have a deformation of 1 inch or 2 inches. You can design for that and you can have a spread footing. But beyond that, you are just well served to stay away from it. You take your design decision has to be using the foundation. So use piles and take them through any of the liquefiable zones. And it's not always that there is one liquefiable layer. You might have this crust, liquefiable layer, then good soil, then another lens of sand and silt, that's going to liquefy. So you want to be deep enough that you have taken your pile down enough that if whatever liquefaction is going to happen, your pile is further down and it can develop the vertical and the lateral capacities based on that and ignoring wherever the liquefaction is happening. Otherwise, your structure is going to walk on you. Okay? So, deep piles that extend below the zone of liquefiable soils. And these foundation elements have to be designed to withstand the predicted ground movement induced loads. So as the ground is moving, it's putting some loads onto these piles. You can also do some soil improvement. So you can densify and remove and replace and de-water, blah, blah, blah. You can do a lot of these things that you can, so that you can control liquefaction as best as you can. And then also look at the bridge superstructure to make sure that when your foundations are moved so much, what is happening with the superstructure? That's quite important. So really the idea is that you either have a structural solution, i.e. you have piles that are strong enough that can take the loads and won't move too much so your bridge alignment is good, or you go in, if it's not too extensive, you do ground improvement and then maybe you can get away with smaller sized piles or you can have spread footings, or you have a combination of the two. So you do a fair bit of ground improvement, but you still need some sort of structural solution on top of that. What I've seen is in a lot of the situations, you end up with a hybrid solution. You will do some ground improvement, you'll do piling. And the evergreen line on some of the sites, there were just so many utilities and we were in such a constrained corridor that we could not do any meaningful ground improvement. The geotechs were very clear, they did their studies, and they came back and said, we cannot do ground improvements. You guys have to find solutions that are structure and pile based and make sure that you achieve your performance. So that's why I say it was challenging, but also quite fun. So these are the three things: design the piles to resist the forces. If sufficient pile strength cannot be achieved, assess if your structure can tolerate the anticipated movements with some limited pile plasticity. And then if that's not the case, then you carry out ground improvements. Usually you do either a hybrid or a structural only solution. When there is deep-seated liquefaction and high probability and high movements, you cannot do ground improvements very easily. It becomes very cost prohibitive. So if you've got a layer 30 meters into the ground and 5 meters deep, that's going to liquefy. What are you going to do about it? It's quite difficult. So this is from ATC 49. These are the two different cases, as you can see. You've got non-liquefiable soil and liquefiable soil. So when the soil moves, it's got this displacement profile, your pile bends like that, and it's got to be able to take that. Now this is quite different when you have a non-liquefiable zone, a liquefiable zone, and a non-liquefiable crust. So the liquefiable crust is going to move, and it's going to push the whole pile with it. So over this short length, you're going to have an extreme demand on curvatures. It's going to become quite difficult. So be mindful when a geotech tells you you've got liquefiable layers and you've got a crust riding up on top. You better pay close attention. I know this it seems a little bit messy, but here is one way of dealing with it. So this is a global model. This bent has two columns. Then you have bents with single columns. So I have in this snapshot about 6 columns. I've got multiple piles underneath each column. And then I've got these PY curves that are attached all the way up and down with vertical curves and the base curve, okay? And the way we do this now is the geotechnical engineer is going to give me a ground deformation profile. Just as this or this, it's going to tell me that at this depth, your soil is going to move by this much. It's going to move by 50 mils, it's going to move by 100 mils, and then it's going to move by 200 mils and 500 mils, and it's going to continue like that for this many meters.
And that will be for how many years of recurrence of earthquake?
So that we look at 475, 975, and 2475.
That's instruction manual has to ask them.
The geotechs in Vancouver are very smart. They've been dealing with this problem for 20, 30 years, so you don't have to really. Now, if you're dealing with other jurisdictions, you have to ask for a lot of those things. But there's so much wealth of experience on the West Coast here that this is, on any project like this, it's just automatically, they know what to give you. Yeah. So, and that's a good thing. Like, we learn from each other, the structures and the geotech. So there's a lot of interaction that happens here. A lot of interaction. And certainly this evergreen line would not have happened if we hadn't collaborated so closely. We were meeting pretty much twice a week with each other. Okay, so the other thing they'll do is they'll give me liquefied PY curves. So the PY curve of virgin soil is different. Once it's liquefied, its strength has decreased. So I might run my inertial analysis based on this PY curve, and I might get a PY curve down here for my liquefiable soil. And one should ask for liquefiable springs. Why? Because their stiffness is lower, okay? And they'll plateau out at lower force level. And because you're gonna force your structure to feel that, if you use this, you're gonna put a higher force in there. Okay, so be mindful. They usually, well, in Vancouver, they know, so they give you two sets of PY curves, the liquefiable curves and the non-liquefiable curves. For the inertial analysis, we use the non-liquefiable curves. For the liquefied analysis, we use the liquefiable curves. So what we do, as I was describing before, on a pile, we have a spring, and this side is fixed in space. This side is attached to the pile. I will have been told that this point moves 100 mils. I'm going to go and create a load case where I'm going to push this point 100 mils. And the 100 mils is going to act through this stiffness and apply a force onto that point. And if it has plateaued out, it has plateaued out. The program takes care of that. If it's still somewhere here, then it'll apply that. So you can see that now the trouble comes in because of non-uniformity. As you move up and down, the ground profile, the deformation profile changes. As you move from pier to pier, it also changes. So it becomes a very complicated problem, and that's why you need a model that's capturing this sort of a level of detail to do that. The one thing that can happen now, if your liquefiable zones are down here somewhere, you might be forming a hinge within ground, right? Because that's where the load is coming from. The inertial load is generated up here. This, I'm just simply looking at my liquefied performance. So I don't know where that's going to happen. So how can I figure that out? Well, I need to have my PM curves for all my piles. I have to know that because I got to know the capacity. The way you can do that is first run a linear analysis with all the deformations applied and look at the bending moment profiles of your piles. So this is the application of the ground deformation load. So you can see here, the liquefaction is rather shallow. So here the soil, only this much of the soil is liquefying, whereas here it stays pretty high to about this point, and then the point that the numbers are quite small. Okay, and then that's similarly the case moving back. This is the global displacement of the structure. You can see every one of these has been pushed to some extent. Okay, but what you want to look for is this. So you can see where the maximum bending moments are happening for each location for those deformation profiles. Now you know if it's going to hinge, that's where the maximum demand is. That's where it's going to hinge. So now you go and put a plastic hinge in your model at that location. Okay? Yes?
Even the moment is less than the yield moment.
So if the moment is less than the yield moment, the work is done. Right? Then you don't have to track your plastic rotations. You don't have to track anything because you're staying elastic. If it is higher, you know where it's higher. Right? Now you can intelligently go and rather than, you could do it brute force. You could put a plastic hinge everywhere and just let it run, and then it's going to run forever, right? But this is a slightly better way of doing it. These are the shear forces. So you can see that this structure has enough of a pile length that by the time you get down here, your moments are completely out of the system. Now imagine if you had stopped your pile here. You would see an instability in your system. Your analysis would not be running. It would just start to track. It would go. So your piles have to be deep enough to take you out of that zone. So I think the one thing we should take away from this is a bit of an iterative process. Okay. Also, the length will depend on how much axial load you're going to see. A lot of the times the length is dependent on the vertical load. So maybe if you put the pile only to here, this bending moment would be higher and then it would die off. That's fine, but that might not be enough to develop the pile vertically, which means it would sink. So the two things go hand in hand. You've got to look at both things very carefully. So these are just the shear forces that I was describing. These are the axial loads due to the ground deformation loads. And if I could have done this in a better manner, you could see that by the time you get here, you've taken the load out of the system. But if you were to shallow these up, you would run into problems. The way we do this a lot of the times is we'll run our analysis and we'll come up with our axial loads. We'll run it in our structural software. Then we'll also give the loads back to the geotechnical engineers, so they use the geotechnical software where they can capture the soil more appropriately to confirm that the vertical length of the piles is appropriate. So on such projects where a lot is riding and it's multi-million, hundreds of millions of dollars, you need to go to that sort of level of detail. Now there is the cat amongst the pigeon amongst the cats. How do we combine inertial and kinematic? Because I want you to think about it in a time sense. Okay, so the earthquake comes along, it starts to shake the bridge, the pore water pressure starts to build up. At some point, while this shaking is going on and the bridge is responding in an inertial fashion, the soil also starts to flow. So now your piles are not only, or your structure is not just resisting the inertial load, it's also resisting the soil flow, the kinematic load, or the vertical displacements that are going to happen. So if you're doing a true time history analysis in FLAC, where you've got all the nonlinearities in your structure and you've got all the nonlinearities in your soil, fair enough, that analysis is going to run until I'm 60 years old. Okay, so, and in all probability, you will not have the budget to run that sort of an analysis. So how do we go about the combination? Okay, when you look at our code, it's basically silent. If you look at ATC 49, which is one of the original documents that address this, it says you don't need to combine the two together at all. So you run your inertial analysis and assessment and make sure that your performance is met. You run your kinematic or your liquefaction analysis separately without any inertial effects and make sure that that's fine. So this was back in the mid to late 90s. By the way, the jury is still out on this. There's still a lot of research going on. But we know that there will be some overlap. The liquefaction will happen. It's not like the earthquake has already stopped. But it's highly unlikely that the maximum inertial is going to happen when the maximum kinematic is happening. There's sort of a physical reason that I can think of that makes it unlikely as well. The inertial demands are highest when you have more stiffness in the system and the soils are able to bring the earthquake motion and energy through and up into the system. Okay? So once you've liquefied, it also starts to act as a bit of an isolation layer. So all the inertial effects are not able to filter through into your system. So when the inertial is at a maximum, you haven't quite liquefied that far because you're still getting a lot of high inertial loads because all the earthquake energy is coming through. Once it's liquefied, that starts to diminish. That starts to dampen out. Now it's more the soil that starts to move against or downwards or against the pile. So on the Evergreen line where we were told to combine the two without telling us how to combine the two, I had to do a fair bit of research. There's a Caltrans-based document. They've done a lot of centrifuge testing, and they basically say you need to do the 100% 50% combination. So look at 100% kinematic at 50% inertial, and use 100% inertial plus 50% kinematic. And this is, I think, where the practice is going. In the new code, this is not going to be mandatory, I don't think, but this thing is mentioned in there as a suggestion. I know that the BC Ministry of Transportation is working on a liquefaction design document, which will become part of the state of practice. It will be implemented by the Ministry of Transportation. It will be mandated, by the Ministry of Transportation that all designs use that. unless there is reason to believe by the geotechnical engineer that we should use 100% plus 100%. In which case you'd have to use 100% plus 100%. So how do we combine the two? This is a little bit of a blurb, but so you run your inertial separately, and you run your kinematic separately, okay? And these are all in your global models, you can run those. When you combine, the one way we came up with was to isolate each bend, okay? And you apply the ground deformations to the local soil springs as you've done in the global 3D analysis before. Now, when you do that in a single, on a single bend, you have lost the effect of all the continuity, all the other, the deck is not there, so the interaction between different pylons or different piers is lost. So when you apply those displacements, your bending moments and shears are not going to match your global model. But what you can do is go into the global model and get the shear and the bending moment and the axial loads from the global model. So when you apply these ground displacements and those reactive forces, you'll see everything will be in equilibrium. And that's how you've now captured that state, right when the 100% kinematic happened. For the inertial, if you were moving, say, 50 mils, now you need to capture this state from the 100% kinematic, and now you push the top of your column another 25 mils to do the combination. So in a quasi-static way, just using pushovers and not having to resort to nonlinear time histories, which were not mandated and we didn't have the budget for it, that's what we came up with. So this is what this whole thing is describing, and you can read that. So this is a separate model where the pier has been poured out, and you apply the ground deformations, and then you go and apply the shear load at the top of the column, and you'll see that all of a sudden everything is in equilibrium. You look at the moments, they will match what you get out of the global model, okay? Then you take that as your last stress state, and you do another pushover starting from that point. Now you push the column, whatever 50% of the inertial that you've calculated, or you can push it 100%. So that's how you come up with it, and then you can look at the bending moments and shears, and if there are any hinges forming in the piles, all of that stuff can be looked at. And so you realize that this is a bidirectional issue, but you only push it in one direction, so you can, on the one side, it's going to be different, the axial loads, than the other side. But then, of course, the reverse. So here you see the bending moment in the piles. This is a little bit better, so you see how it kind of just goes to zero. So in order to capture the actual behavior, we have to, if we think that the capacities or the demands are higher than the capacities, we have to model the plastic hinges as well, which from the global model you would have got. So shear distributions, and that's how you can do this sort of complicated stuff just using pushovers and not have to resort to a very expensive FLAC analysis. Because using a purely structural software, you have no way of accounting for the soil stuff, right? Because it's going to build up, it's going to start to flow at a certain time. FLAC will account for all of that. But it's a 3D finite difference model with lots of complications in the soil elements. They're like true finite elements, or they're they're not like just single line elements or whatever. And then you've got to input proper soil degradation models to make sure that the soil, that's a very specialized field, and it's a geotechnical field. So we tend to get the input from our geotechnical friends. We do this. We'll also give these back to them to kind of see if from their software they can get results that are quite similar, and we were able to do that. So the code, just to let you know that when it comes to single span bridges, I'll quickly just give you a minute of a summary of each. It doesn't require any real analysis for single span bridges, except for if you have truss bridges. Then you have to design them elastically with an R value of 1. You have to provide minimum support lengths, and then you're done. But then when you go to clause 4.6, it says you have to do the foundation design. So when you read chapter 4, it almost seems like you don't need to do any analysis. You go to chapter 6, you've got to design the foundation. So if you don't know the force, how are you going to come up with the foundation design? One way of doing it is just taking your spectral acceleration on the plateau, multiplying it by 0.8 times the weight, which is kind of in the code, and you take that as your base shear to design your piles. Yes, sir.
Is it, why do we say that this is single span? I mean, it could be 50 meter, it could be 30 meter.
Yeah, the code doesn't differentiate between, like, based on the span length, and there is a reason for that, right? Like, it's your load path it's going to work in the first mode, and what it says is you just need to design the connections to take that 80% of the plateau force times the weight. And when you've done that, you're fine. But it's only for girder bridges, right? For truss bridges where the load path is very, very different, that's not the case. You have to actually look at the design. You have to analyze. But then at the same breath, it says you have to design the foundations. So if the 80% of that spectral acceleration is way too high, your foundations might get killed. So you might have to run a response spectrum analysis to get appropriate numbers to then. Shear keys you can design. A lot of the times we go and when we don't have enough of a support length, we put restrainers between the superstructure and the substructure. This clause will tell you what to design those restrainers for. This clause is for the minimum support length. That basically tells you how much of this N you need to have. It's got certain values there. This is something that the code is basically silent on, but we have to look at this. This is the joint shear. This is when the column and the cap, where they come together, that joint zone. It's a principal stress issue. So you have axial load and you have bending moment and shear. So you've got shear stresses and direct stresses that are acting on that infinitesimal element within your joint, and you use a Mohr circle calculation to come up with the principal stresses. And if they're below certain thresholds, then you're fine. You can just carry on with life with some minimal reinforcement within the joint. But if you find that the joint is going to crack, then you have to put in more rebar. So be mindful that that needs to be looked at, even though the code doesn't give you a whole lot of guidance on it. However, you can go to Priestley's book, or you can go to ADC documents or the Seismic Design Criteria document by Caltrans, and it's quite well defined and codified, so you can look at that. The column shear we've talked about. So let's have a look at this McDonald-Cartier bridge, which is in Quebec City. And it's a girder bridge. It's a 2-girder bridge. And we did some assessment and retrofit on it. So coming into the home stretch for the last hour and 15 minutes. This is what it's showing: 2-edge girders, and then you've got these floor beams, and then the slab that kind of goes between them. Okay, so this is a 618 meter long bridge with fairly long spans, as you can see, and an overall width of 30 meters. So it's quite a wide bridge. It's got non-prismatic 5-span continuous built-up steel box girder, and that means that it's changing its depth. It's non-prismatic. This is what it looks like from the air. I'm trying to remember the 2 sides that it joins. It'll probably come to me. So they had a history of inspections and studies and repairs and rehab on this structure. they carried out live load and seismic analysis. This is before I got involved with it. So vertical loads, gravity loads were fine. The structure didn't have a big issue. And then for seismic, they did a multimodal response spectrum analysis to start off with to see how this would behave. It had various deficiencies. These rocker bearings, they have fallen out of favor a long time ago because we've had lots of failures of these, and bridges have fallen off the rockers and these pin bearings. The big issue here was there were wall piers, massive wall piers, that had inadequate capacity under seismic loading in the longitudinal direction. So they were shown to have rocking. So they would just, the foundations would lift up, and we did not think that this was a mechanism for this bridge that you could rely on. And in a significant seismic event, the longitudinal displacements would be quite large, and there was fear that this thing would just become unstable. So this was back then. The owner wanted to seismically retrofit it as a lifeline bridge and improve the functionality and geometrics of the bridge. Fair enough. So the issue for this one particularly was it was only Pier 2 at which you had a shear connection between the superstructure and the substructures. Everywhere else it was pretty much floating. So all your seismic load longitudinally would go to one pier. Okay, so the first thought was, why don't we share the load and we put shear connections between the superstructure and the substructure at different locations? So this was the conventional retrofit strategy. It basically said, well, let's replace the bearings at piers 2, 3, and 4 with part bearings that are able to transfer the shear, and then we will start to have load sharing between the piers. It's not just going to be one pier. When that happened, the pier demands could still not be brought down below the elastic values. And what that meant was the contractor, the design had to be such that you had to stabilize those piers and you had to strengthen them. Now you're going through a pretty big, deep river, and you'd have to put in lots of complex, costly in-river pier works, which would have driven the cost of this thing up in a big way. Okay, so then that brought us to the base isolation strategy. And this is one of the examples where that can help quite a bit. If you could see, the bridge had stiff piers, so short period of vibration, pretty much checking off all the three boxes. It was highly non-regular, with piers having different heights, so different stiffnesses in the system. And when you look at the Montreal seismicity, again, there is more rock there. And so the ground motions are more rich in high frequencies or low periods. Whereas once your periods are large, your energy drops quite a bit. So now you've got a real case of doing some base isolation, because you can get away from stiff piers, you can regularize your stiffness, and the ground motion side of it was also such that it had more high frequency content. So if you moved your period away from it, you'd see less response from the system. So those three are basically given right there. So, you know, it's more driven by shallow crystal events, except for the Gatineau abutment where we had the so this joined Ottawa to Gatineau, I think, or yeah. Okay, so what happens with these base isolation bearings is they give you some flexibility, they lengthen the structure period. And as I was mentioning before, the issue could be that now you have increased flexibility, which means more displacement. So you have to control that. You can't have your displacement becoming too large. Okay, so the performance criteria at the time, this is pre-S614. Keep in mind that even in S614, when you're retrofitting, it's up to the owner to decide what performance the owner wants out of your bridge. It is almost impossible for these very old structures to be brought up to the current code standards. You will end up spending so much money that you you can do a new bridge for cheaper than that. So the cost implications are huge. It just doesn't work. So even the new code leaves it up to the owner to decide, given their risk profile, how much money they have, to decide what level of retrofit against what return period the owner wants to have. So that's where they engage us. That's where they engage people like us, all of us in the room, the engineers, to get some feedback. Like, they have a pretty good idea of how much money they can spend, and we can come in and say, well, for that much money, you're asking for too much. It's just not going to happen. To get to that, you need to spend this much, and then the next question is, well, can I just build a new one for that? Okay. So in this case, that wasn't going to be, with the in-river run-of-the-mill typical strength-based retrofit, the money was too much. But if we could just move the period away, we would be able to, the thought was that we wouldn't spend too much money. We wouldn't need any strengthening of the piers. The load transfer between the substructure and the superstructure would be quite small. We'd make things work. We wouldn't need to do anything in river and on the pier. So that was the thought. That's where we started. So it was required to have full operation for 475-year event and just emergency vehicle access for 975-year event. When you look at these bearings, isolation bearings, you have the lead rubber bearings. You can also use the usual suspects, the rubber bearings with the steel shims, although you have to get a lot more testing on them. You can use the friction pendulum bearings. The lead rubbers tend to have a bit of an issue with cold weather. We were in Montreal, which is quite a cold place. So the thought was to go with these friction pendulum bearings. They have excellent energy dissipation, and they also have this self-centering characteristic because you climb up on this concave surface and then it naturally brings you back. So the idea is that after the earthquake is over, the structure can actually just come back. It has that restoring force to bring it back to where it needs to be. So they do exhibit consistent performance over large temperature ranges. They are dependent on how much vertical load they have to carry. Their stiffness changes and all that, so you've got to look at that. Because we were trying to regularize things, your piers had more load. The abutments had less load, obviously, because they're taking half a span. The piers are taking a full span, each one of them. So we were looking at two different friction pendulum sizes, one for the abutment locations, one for the pier locations. So this was the response spectrum. This was funny because we asked the geotech to produce the 1 in 975-year site-specific spectra, and the site-specific 975-year return period spectra were smaller than 80% of the 475-year return period event. And at that time, the S606 code basically said you can come up with a site-specific response spectrum, but it has to be at least 80% of what you come up with based on the code. So here we had a pretty funny situation where the 1 in 975 site-specific was lower than 80% of the code spectrum for 475. So what we decided, we wanted to go to that, but the owner was not willing to drop it that much. And they said, you just use 80% of the 475 and design everything for that. So that's what we did. We got 5 sets of spectrally matched time histories for the whole bridge. And this is what I was showing you earlier. The Gardiner abutment is founded on 66 H piles. So it had a different set of records that were matched to the soil properties. All the other ones were matched to rock conditions. Okay, so this is the overall model. I was just showing you, if you remember, I was just showing you a blow up of this little area here before. But this was the whole bridge, the 5 spans. It has a little end span there and a little end span on this side. Okay, so we used a 2% value for the isolated modes, and for the non-isolated modes, we used the 5%. Then when you look at the additional damping from the bearing hysteresis, if you were to do a response spectrum analysis, you'd have to bump it up artificially because we were doing a nonlinear time history analysis. That's accounted for because you are explicitly modeling the hysteresis and the energy is being dissipated in there. This is where we used the fast nonlinear analysis, which is modal. So we used 306 modes for the solution basis. We found that those were adequate for shear and flexure demands, but we were getting some unrealistic torsional demands, which we didn't believe. So we thought that that was just a numerical issue and the actual demands were not that high. So we ran 1200 modes and then we found that the high torsional values just went away. But that was taking a long time, so we just ignored the fact that the torsional values were high because they weren't high. We proved that. And so all our analysis was then based on the 306 Ritz modes. So the approaches on either side, there's the big bridge that moves, and then there's a short span at the end. So the tendency is for the big bridge that's isolated is to move a lot. And if it's attached to the end span, it can really drag it with itself. So we came up with an idea of putting a specialty joint. So there were existing finger joints, but because this would get isolated, it would move a lot more, and the finger joints would basically bind up and try and grab the end spans and also bring those along for a ride. So we effectively disconnected the main bridge from the two end spans. So you can order specialty seismic joints that have a lot of displacement capacity transversely and longitudinally, so that now the end span is doing its own thing and the main bridge is doing its own thing. And the joint just lets them be decoupled from each other so that there is no interaction. Yes?
I see here you use a Reese mode, not the eigen mode.
Yes. So it's because when you look at the fast nonlinear analysis, it's based on Ritz modes. That whole methodology is based on Ritz modes. So if you want to read a bit of the background, that's what I was saying. If you go to the CSI website and you Google fast nonlinear analysis, it's based on Ritz modes. The thing with Ritz modes is that they come out of your actual loading. So they're load-based.
Yeah.
Okay, so that's why they converge a lot more quickly than using the other ones.
Yeah, then which load you have considered for their so many load pattern here.
So that load pattern is really just a transverse load pattern and a longitudinal load pattern. That's how it's just the derivation of the load, the mode.
No physical load, only the reaction.
It's just that the notional load that helps the program come up with the Ritz modes. It's the same thing. So it's a much longer and more involved conversation. We can have that, but if you want to read first a little bit, go to the website and read through it. And also, if you go to if you go to Chopra's book, there's a whole section on Ritz vectors and how they work. Okay. Okay, so then our base isolation analysis assumed no interaction between the approach and the main spans because we isolated them. We were going to physically isolate them. So now we ran the approach span separately, and it had the two caissons on the one side and just a wall on the other side with short reinforced concrete or pre-stressed concrete girders. And what we found was that the abutment piles were just seeing really high demands. And we scratched our heads for a while, couldn't figure out what was going on. We thought that we wouldn't see that much of a difference. So we had got our matched time histories from the geotech engineer. And when we were running the response spectrum analysis, we were getting demands that were several orders of magnitude lower and things seemed fine. But when we ran the matched time histories, all of a sudden, things were just blowing up. We weren't sure. So several days of just looking at it and not figuring out what was going on. The engineer who was working with me, he had this brilliant idea. He was a bit of a computer whiz, which I'm not. He zoomed in using MathCAD to see how good the matching was. And here you see the this is the site-specific, these are the site-specific spectra that the response spectrum for the time histories have to be matched to. At 0.2 seconds, it wasn't a good match. Like, this is a factor of 6 higher. But when you looked at the whole thing, this peak was lost. You couldn't see it. But locally, it's a big peak. So that's when we clued in that there was a bit of a peak. When we looked at the modal analysis, because this is a very short span, its fundamental period was sitting at 0.2 seconds. And then with matching at 0.2 seconds, the matching is really bad. It's up there. That's how we found out that our demands were artificially high. Okay, so you couldn't, if you zoomed out further, you couldn't see it. So anyways, after we dealt with that thing, you see before base isolation, your peer 2 was sitting at 1.46. After base isolation, you can see that some of the D over C's have changed. 0.5 has dropped to 0.3. 0.4 has gone up, has dropped a little bit. 0.26 has dropped. The big one was 1.46. That's dropped to 0.22. So you can see that after base isolation, everything has gotten better. So in the longitudinal direction and the transverse direction.
I'm sorry. You guys have changed the carbon scale?
So what we did to solve that, once we found out that that was the case, we just dumped the whole nonlinear time history part. We just ran response spectrum analysis, and it showed us that we were all elastic. So we just got rid of that artificial peak, because we could see that it was artificial, but it was so localized that, we didn't bother going back. And this wasn't part of the big bridge anyways. This was just a short M span. And we argued with the owner, looking at the code, that for a short M span, we didn't need to do a nonlinear time history analysis. Plus, the response spectrum showed that it wasn't going nonlinear.
It wasn't artificial, it came from the ground motion, right?
Yes, but that peak is artificial because the program hasn't matched it to the actual response spectrum properly. It's matched so that it's like 6 times higher. That's why it's artificial.
You can't fully match a ground motion spectrum to the targets. You always have peaks.
Yeah, you have a little bit of peaks, but then this is just a very localized phenomenon, right? So as soon as the 0.2 seconds goes to 0.3 seconds, it just goes away. So there were several reasons why we said that there wasn't really any value in it. Because now you're looking at a dinky little end span, and to just keep spinning your wheels was just not that big of a deal. Okay, so shears, you can see they're also fine. This is okay. So we were still seeing a little bit of an overstress, 20% overstress in just from a purely elastic B over C point of view in the piles, whereas previously it was like 5 or 6. 1.2 means your R value is like 1.2. Right, so it's asking of a very little displacement ductility on part of your piles. It's almost elastic, and this was deemed acceptable. And we said we're not going, because there are 66 piles overall. There is so much room for things to redistribute. We're not going to do any kind of strengthening on the abutment. If this were showing up as 3 or 4, we would have gone in and done something about it. Because even within steel, you yield and then you have some post-elastic strength anyways, so we just stopped there. So I've kind of talked about this, different bearing sizes, specialty joints. We did put new elastomeric bearings for the approach span because we want to get rid of the older bearings. So in summary, when we ran the response spectrum analysis, it showed bearing and pier deficiencies. Could have done a conventional retrofit. That would have been very costly and also quite difficult to accomplish because you've got a big river that's flowing underneath. So came up with this idea of seismic base isolation. use the fast nonlinear analysis with Ritz vectors. Because this was S606, we only needed to use 5 time histories. We were able to reduce all peer demands below their elastic capacity values. The Gatineau approach showed resonant response based on the free field time histories. So that's the other thing is, these time histories are all free field. So if you were to run a coupled analysis with a forest of piles, you're going to see a very different time history. Because when the soil and the piles are interacting, it's going to reduce the effect. And with only a 20% margin, those are the kind of decisions a lot of times we have to make in real life, because you know the consequences are simply not there or tolerable, and you move on. Okay, so we went back and we just reevaluated based on the code response spectrum. I have a paper that I can share with you guys. I'll send you a paper for this one, and I'll send you a couple of papers for the evergreen line. I've co-authored a couple of papers. Okay, so the evergreen line now. This is a transit line in Vancouver. We had a total length of about 11 kilometers, 7 stations. It had vehicle storage facilities, 80 kilometer an hour speed, about 1.4 billion. And I think, well, it was supposed to open in 2016. Not sure exactly when it opened. It had at-grade sections, it had a tunnel section, and it had elevated portions. So amongst the elevated portions, we had the standard guideways where you just had the concrete pre-stressed tubs basically. But then and those are all simply supported spans. Those were in areas where there was little to no liquefaction. And then we had special structures which were continuous, anywhere from 4 or 5 spans to 8, 10, 15 spans. My company at the time was involved with the design of the special structures, not the regular structures. So when you look at this, it starts. It's an extension to the Millennium Line. It goes through here, starts at Lougheed Mall, and it ends in Coquitlam. So it's really an extension of the Millennium Line, but we call it the Evergreen Line. And so here is a bit of a rundown. The blue is elevated guideway. The yellow is the tunnel. So anywhere you see blue, that's an elevated guideway. The yellow is the tunnel, and the green is ground level. So you can see this is all elevated. That's the tunnel, elevated, at grade, elevated, at grade, and then elevated, and then ends at Douglas Station, or Lafarge Lake Douglas Station. This was also a performance-based design. Our alignment was running through some enormously challenging soil conditions. And liquefaction-induced lateral spreading was a critical design issue here. This was the biggest issue that we had to deal with. We couldn't really do ground improvements for the most part because of deep crust and right-of-way issues, lots of utilities, so it was very difficult to do that. The ministry came up with a slightly different mechanism for delivery, and I think it had perhaps to do with some of the past project experiences that they had where there was some litigation involved. What they told us was that we were going to have to report to a seismic peer review panel, as later the acronym was used more than the actual term, so it's the SPRP, Seismic Peer Review Panel. And for any portion or for any structure, we had to prepare a seismic design strategy memorandum, an SDSM, which was a report that basically provided them details about how we were going to achieve the performance, what level of analysis we were going to use, how we were going to analyze things, how we were going to show that we had achieved the performance with strain limits, with rotational limits, whatever they had in the project agreement. So that was really good. At least we had somebody to go to and cry, right? It wasn't like we were dealing with people that were bureaucratic and they didn't know anything technical. So that was a good thing. The issue was that the seismic design strategy memorandum was necessary. It was necessary to get it approved before you could do any construction on site. And if any of you have ever been involved with design build projects, they're really build design. So you're almost designing when the contractor has mobilized and it's already working. So you could not break ground unless the SDSM had been approved. When they thought about it, when they wrote the PA, the idea was that they would ask the engineer to do some back of the envelope calculations, some simplified calculations to show that the system that they were coming up with was going to meet the performance criteria. Make that part of the SDSM, get approval, then carry out the design after that, after you've got that initial approval, and then take it to design after you produce the drawings. The issue was that the conditions, the soil conditions were so challenging and the structures were so complex that you could not do some simplified analysis like I'm going to do a single mode analysis here and I'm going to show you that, you know, my R value is 1.25, so I'm going to be okay. And I kind of picked up on that pretty early, and I had this in my head that this was going to be a bit of an issue. So we were meeting with the seismic peer review panel every Wednesday. And I started telling them sort of early on, I was telling them that this was going down a path where, you know, simplified analysis were just not going to give us any real confidence that our system was going to work. And that by the time we would have it in hand, our design would be quite advanced. And we'd have to do fairly detailed analysis to basically show that we had a good system, that our performance criteria would be met. So that was a challenge. I mean, we had to deal with it. I've described this to you. So the panel could approve or reject the SDSM, or they could ask us to do more work. So when I started giving them some results or started giving them open-ended answers, they weren't happy. And I said to them, I told you guys that this was not as slam dunk as you thought it would be. Okay, so I'll skip this, but we had some permitted and potentially permitted earthquake-resisting systems. We were allowed to use ductile reinforced concrete columns and braced frames and moment-resisting frames. If we were to go use some base isolation strategies, then we'd have to get their permission first. Okay, and then potentially permitted. That was also permitted, but potentially permitted where we had to go and seek permission on a case-by-case basis was some minor inelastic action in the piles. So in-ground pile hinging with minimum plasticity, we'd have to go to the panel every time and get their buy-in on a case-by-case basis. This I think I've shown you before in the very first talk. We had different performance levels. This is really what we were dealing with, 100-year immediate use and 975 repairable plus subduction repairable. But the issue was liquefaction where it was quite difficult for us to get that going. What we had to do was the original steel strain for the immediate performance was 0.002, which we just simply could not make things work with. So we were granted, we asked for 0.01, we were given 0.005, but even that made a huge difference. Just that little bit of inelasticity, it made a big difference. We were able to make it work. The repairable performance rebar strains were even more ridiculous. So you had 0.002, and for a 30 or 35 M bar, I had 0.0086 to work with for repairable damage. Absolutely impossible to do that. Right now, in the ministry supplement and in the coming code, we have 0.01 for minimal damage. Here we had about 0.007 to 0.008 for repairable damage for 975. It was just never going to happen. So I went there and I cried. I didn't cry, but I had to engage them for like several weeks and give them lots of reasons and research and show them lots of different things. I asked for 0.05. You know how that give and take happens. I was given half of this and I was given half of that. And they said, okay, well, in the project criteria, there is no mention of a 24-75-year return period event. And we're not going to ask you to run an analysis for 24-75, but we want you to show us that you at least have, you're only at 67% of your ultimate capacity at this point. So that if a larger earthquake came along, you still have about 50% left in your system. So they tagged that on to this requirement. So we had to show that we had a reserve beyond this. Okay, which was fine. We were able to show them that. Then the piles were all in terms of plastic rotations. Their performance, we proposed the values based on ADC 49. Then the pile inelastic response limits, as I was saying, wasn't defined by the project, so we used ADC 49. It has life safety performance requirements. It tells you if you have a concrete pile or a steel pile, these are the plastic rotations that you need to be under, but it had nothing for repairable performance. So we proposed 60% of the life safety for repairable, and that was approved. So that's just something that, you know. So there we go. But my number wasn't wrong. So 0.0086 for 35 bars. It wasn't going to happen. And I showed them this. Anyways, we arrived at those and we were able to carry out the design. The issue then again was, how do you combine kinematic and inertial? We said we were going to use, or we proposed based on the Caltrans document that was brand new at that time, I think. 2013 it came out, we were going to use kinematic plus minus 50% of inertia. And I've described how we did this. I've already talked about that. So that's just about that. The other issue that we came up with, or that we had to resolve, was where the guideway came into the station. So if you read the project agreement or the terms of reference, the station design had to be based on British Columbia Building Code, BCBC, which is just a copy of the NBCC. And I'm sure that most people here, or everybody is familiar with that. It's a force-based design. So you have your R values, and that's what you use. Now, you've got that. In comes the guideway. Guideway has its bend, and the guideway sits on the bend, and the station sits on top of that. So the bend is now, it's a support for both the guideway and the station building. So this is an intercultural marriage where the two partners don't even speak the same language. They're completely just out there. So what do you do? And so that's where we had to collaborate quite a bit with our building friends, people that were designing the station structures, and we had to really address the design inconsistency. BCBC is based on 2475 force-based design. This is based on 475, 975 performance-based design. There's no way to marry those two together. However, they were married together. So what we did was we said, okay, what are we going to do? We're going to design the guideway bends that are supporting the fixed facilities, i.e. the stations, to the guideway criteria. We're not going to use our values. We're going to do it based on 475, 975 subduction with strain values and rotations and curvatures. We will do that. And the on-ground fixed facilities that were not, the portions that were on ground that were not supported by the guideway bends, those were designed by BCBC. So that was sort of the happy medium that we kind of got. Our basic design solution, given all the the liquefaction and the variability was to use large diameter concrete filled steel pipe piles that basically pass through the liquefiable layers, and we put them on competent strata to get the bearing strength. We had to use variable foundation flexibilities and superstructure articulation and different column sizes to fine-tune the design, to save money for the contractor, all of that. Our pile diameters for the guideway, they varied all the way from 3 feet to 6 feet, or 914 mils to 1830s. And we did find that with these piles and the strict limits that we had on potential plasticity in ground on different sites, that with these sizes we were able to withstand the variable liquefaction and passive pressure issues due to the crusts. Our designs were tailored to that. So Rycold is a structure, basically something I was talking about, and this is where you have foundation soils that change from very stiff to highly liquefiable in a very short distance. So this posed a significant challenge for foundation design because it was getting to be very, very non-uniform. So we had to iterate quite a bit. At the first pier location, which is 60% of the liquefaction value, we made it as soft as possible. Okay, so we wanted it to kind of not be a very stiff point. So we used 4 762 millimeter piles. And then as we got away from it, we started to use bigger. So these are 4 feet, and these are 6 feet. No, this is 3.5 feet, I think. Yeah, 610s and then 762s, and then 912s. So then the other thing we did was we broke the superstructure at the first pier. We broke it in the sense that over here we had an expansion joint, because if we didn't, it was cranking, the deck continuity was cranking so much moment that we just couldn't make it work. So we put an expansion joint, and the idea would be that these two things would just go, because this is starting to get more uniform. We didn't want to introduce a very hard point here, so we made it soft from a foundation point of view, and we put an expansion joint so the two would move relative to each other and gave them large seat lengths so nothing would fall down. So this is kind of what the deformation profile shows from 0 to 2.5 meters, 2+ meters. So this is really, really flowing. At 2 meters, it's a number, right? That just means it's flowing. So this is showing you some of the construction. So the idea was to incorporate more flexibility and avoid a hard point so that you don't have that stiffness attracts load happening, and that you have a reduced concentration of local demands. Of course, there would be some concentration, but it would be reduced. So this is where you see this, it starts here or whatever, and then that's the first one, that's an expansion joint, and then it's, this is the next one. This is a Douglas special structure, sorry. Here we had the station as well, and that caused us some issues. You see here that the variability in your liquefaction is huge. So the first two, you see how shallow it is, and it's only moving about 100 mils at the first two supports, and the next supports you're getting a lot deeper and a lot more deformation. So all those things have to be thought about. So the station building was there, and it was becoming a bit of an issue as to how to tackle this problem. So we came up with a ground floor, a big slab, a suspended slab, which was supported on the guideway foundations, the guideway column foundations, with large perimeter beams that tied everything together. And to support the building vertically, we just put 6 10-millimeter piles that were founded within the crust. So really, the building is just vertically supported within the crust, but then the overall load is transferred back into your foundations, guideway foundations that are going all the way down. So we bypass that whole thing. This is a CPR special structure, and you can see this is about 15 spans. Again, over here you've got the at-grade structure, and here they were able to mitigate the soil, so it wasn't going to move much. As soon as you got into this, there's a CP rail, there are lots of things you can mitigate, and there's a lot of liquefaction happening. So all of a sudden, again, you went from no liquefaction to a large amount of liquefaction. So what we did was, this is funny how, I told you guys that we cut rebar out of a column. It's very counterintuitive. In this case, we told or when we collaborated with the geotechnical engineers, we decided that there would be a transition zone in the at-grade section. So they would do full mitigation up to some point, and then they wouldn't mitigate it as much, so that there's a transition zone. So that when our abutment comes into play, it's not like you're going from no movement to a lot of movement. It's now the movement is already starting to happen to unify that a little, or make it a little bit more uniform. So, when you start to think about those things, some of these good ideas come to you. We use some lateral spread profiles based on some refined flak analysis, and the other thing we did was we also put a flexible foundation at the abutment, because the things are still in transition and they're starting to move, so we don't want to create that hard point. When you create that hard point, it attracts all the load to itself. Okay, so we use smaller diameter piles, and then as we moved away, again we went to the larger diameter piles. Okay, so you can read a little bit more on that. So in summary for this part, and then I think I'll show a paper, and we'll probably just wrap up around 3 o'clock. For this one, this was pre-S614, but in the Metro Vancouver area, we've been doing force-based design performance-based design for a long time. Going back over 20 years, especially all our retrofits have always been performance-based design since perhaps the 90s. In a big way, we've been doing pushovers, response spectrum analyses, we've been looking at strains. We've been doing that for a long time. Ever since I've been practicing, which is 2001, I have not come across one retrofit where we've said, okay, we put a jacket now, and its moment the capacity is this much, and the moment demand is this much, and that's where we're going to stop because the R is less than 4 or 5. We've always gone in and we've run pushovers and we've quantified the actual performance. We've looked at joints and foundations and all that. So, and we've kept capacity design principles at the forefront because that's a big insurance for us to make sure that if there is a demand increase or a big change, that at least you have ductility and your capacity protected so that you have a more robust, resilient system. Okay, so I took that on a bit of a tangent, but yeah, this was a multi-level performance criteria, challenging ground conditions, so we had to use fairly sophisticated nonlinear analysis tools. We had to incorporate soil-pile structure interactions. We had to look at directional ground deformations. The geotechs had to see if the soil was going to flow this way or that way, and I think on one of the areas it was going along a vector, and I forget what we did with it, but I think we rotated the axes of our springs to align with that. So but you also see that it's going to move 300 this way and maybe 20 millimeters that way. Then you can just ignore that because you're going to have some reserve in your system. Basic solution, as I said, was large diameter concrete filled steel piles. We took them through and beyond any of the liquefiable layers, and we founded them in competent strata for a robust structural solution. For this project, foundation flexibility and variable pile sizes were introduced. We don't usually do that, but this was an innovation we had to come up with because we did not want parts of the structure that were way more stiff than the rest of it, while the soils were moving in a very uniform fashion. So we had to kind of think about the soil profiles, we had to think about the system, we had to see how it would behave, then we had to show that we were meeting all the performance levels. We also did stuff with the column sizes and reinforcement to make sure that our global behavior was favorable. Superstructure articulation, I showed you one example. Usually for liquefaction, we want to tie things together, but for Rycor, the first span, we actually put in an expansion joint just to make sure that we would not crank that much moment and local demand into it. Another challenge, as I mentioned, was combining the station building foundations with the guideway vents, but we were able to do that. Okay, so for the last few, maybe 20 minutes or so, let's go to this, and I want to show you. This was a paper that I wrote with Mark Gerin, who's a very bright guy, PhD from UBC Vancouver, lots of experience on Port Mann Highway 1 project and lots of other projects. He did all the work, asked me to write the paper, and then said, you can be the first author. And I was hesitant, but okay. We did the first part, and we got that into the IAPC conference in 2017. This was at the Short and Medium Span conference in Montreal last year, Quebec City. But what this paper basically does is, it takes advantage of the fact that most bridges are going to be single degree of freedom systems. And so how can we make use of that and come up with some ideas about how to do some quick design and get some quick performance measures under our belt to see how the structure is going to behave. So I would really encourage you to read this, because Mark had some brilliant ideas. You've seen this picture before, but let's set the stage. So we know S614 is requiring performance-based design now. It's also required for light rail and light rail transit projects. I just gave you an example for the Evergreen line. The way it works is we are looking at multi-level seismicity and performance criteria. Nonlinear analysis is a key tool. You can't just run a response spectrum and R values and be done with it. So what has happened, less so perhaps on the coast here, but generally speaking, even there, it brings a bit of uncertainty for many practitioners. If you haven't been thinking about earthquakes in terms of displacements and deformations and strains and all of that, and basically thinking about it as force, and you've really been doing designs based on the force-based methodology, there is palpable consternation within the design community. You can, and so we wanted to kind of just share that this is a little bit more involved, but the fruit is there. You really can determine how your bridge is going to behave. So we did a parametric study to basically figure out the governing performance objectives. Okay, so there is the 475-year return period event, the 975, the 2475. One of them is going to govern, right? The other two are going to be there. They're more like check boxes, but one of them is going to drive the design. So far, what we've seen is with the 0.002, it was usually the 475-year return period in case of a reinforced concrete vent that was driving the performance. The other two would basically just pose in. So that has been changed, and new criteria have been proposed for S619. So for this study, Mark focused on S619. Okay. So we did that, and he also looked at the correlation for designs based on performance-based approach and the force-based approach. And then there is a bit of a comparison of Eastern and Western Canadian designs. So let me take you through this in the next 10-15 minutes. This is what the new code table is going to look like for Lifeline, Major Route, and other bridges. the service, there is no requirement for the 10% for lifeline because the 5% is immediate minimal. So if you've satisfied minimal damage and immediate service for a higher level, of course, it's automatically satisfied for 10%, and no damage is out because that physically is hard to define. For 2%, service limited and repairable. I think this is different than the new code is going to be different. I think this has been taken out, or something has happened. So I know that in the new code that's coming out, there are only 2 levels for each one of these bridges. And I can confirm for you guys, I can send an email later to confirm what that is. But essentially, we're looking at immediate and minimal, service limited and repairable, versus here that final performance is the first one, and then life safety probable replacement is over here. Okay, so that's what this is somewhat going to look like. This you've seen. I'm just giving a bit of a comparison of the strain limits. 004 and no yielding for S614 for minimal damage. Now we've gone to 006 on the cover, 01 on the rebar. Repairable damage, concrete doesn't come into it because the idea is that you will not be anywhere close to your crushing of the core. And you can have the covers fall off, so no big deal. Because at 006, you've basically got some covers falling anyways. And for extensive damage, the concrete core shall not crush. That was the S614, and the epsilon S was 0.05. And we thought about it a little bit, and then we said, no, we don't want that to be more than 80% of the core crushing concrete. For life safety, we go to 100%. But for extensive damage, we're sitting at 80%. Okay, so we know that we can use the displacement-based approaches for satisfying the different strain criteria. And we've been talking about this, I think, for all of today. Your displacement for the given damage level, the demand, the displacement for the given damage level, the capacity has to be larger than the demand, the design displacement, okay? So for bridges, if you assume the period is t equals 2 pi root m over k, this is the equation for coming up with the equivalent displacement. Okay, so if you just have your spectral acceleration, you can multiply it by t squared over 4 pi squared and times the g, and out comes your equivalent displacement. Okay, so you can use the response spectrum graph, which is in terms of acceleration, but convert it into an equivalent displacement. And this is, if you go 1 over 4 pi squared, you see that you're sitting at about 1/4 of SA times t squared. That's an expression that you can quickly use. Don't worry, I'll pass on the paper so you'll have this. So I looked at perhaps 4 different response spectra. You can see Montreal Class C is the lowest one. Vancouver Class C is the red. Class E is up there. And then we also threw in a site-specific one, which is this green. So these 3 are code spectra, and this one is a site-specific spectrum for a site in Vancouver. And you can see that the plateau stays put out till 1.5 seconds. That's quite a bit, all the way to like, it's sitting at 0.8 G. So we can use the inelastic static pushover to come up with our displacement capacity. The strain limit for each damage level can be related to the top displacement of the column. Of course, for doing that, and I've talked about it, the moment curvature analysis is essential to correlate your strains. Okay, so strains in the concrete and the reinforcement, you can link those to the displacement throughout the response curve. So the way this was done was we produced, and again, like I was saying, you can have a force displacement graph. You can work with strains and go to curvatures, and work with curvatures, go to strains. and come up with that displacement. In this case, Mark chose to go with a moment displacement response and identify the strain criteria on it. So this was just thinking of regular sort of high importance bridges, not lifelines, because you would also need time history analysis. So here you see the moment displacement curve, and what we've identified on there are the different displacement levels. The first one, the green, is when the minimal damage criteria occurs based on the rebar. So that's when the rebar hits 0.01. That's the displacement. Then you have the minimal for concrete. If one were designing for minimal damage, your displacement capacity would be that green line, not the orange line. That's happening afterwards. The second one, you see the repairable for the reinforcement. That's just based on reinforcement. And then for extensive, you can see the concrete occurs with this purple line and a light green for extensive and reinforcement. The first is concrete. So for minimal, reinforcement governs in this case. For extensive, the concrete governs. Okay, so if I were to take 3 lines, I would delete this. I would plot my 2475 or extensive damage line wherever and relate it to this. If it's after this, you haven't met the performance. The repairable, as long as it's to this side, it's good. For minimal, it has to be to the left of the green line. Okay, everybody's hopefully clear on that. So we looked at the governing performance criteria, an equivalent R factor thing, and a comparison for Montreal versus Vancouver designs. So we use just single columns to basically look at the trends and use some typical material properties, F prime C of 35 and 400 MPAs for the steel, and used 4 different column diameters, the 3, 4, 5, and 6 feet. Varied the longitudinal ratios from 0.8 to 4%, and axial load ratios of 5%, 10%, and 15%. So the axial load ratio is P over F prime CAG. Now we know that the natural period is a function of the stiffness and mass. Okay, so you don't need to incorporate any other parameters. As long as you've got the mass and the stiffness, you've got the period. And your performance or your behavior is really just dependent on that and mortar damping. We use 5% damping. So displacement can be primarily related to the T value. So we had a little foundation spring that we kept changing to change the period overall, just to incorporate more or less stiffness. That's how we changed the period. I looked at systems with these natural periods, half a second, 1 second, 2, and 4 seconds. So here we go. We look at the first one. This is Montreal Class C. And you can see which ones are governing the performance. So there's about 623 total cases. The blues are half-second periods. The orange is 1 second, the gray is 2, and then the yellow is 4 seconds. So you can see that as you're you're getting into the longer period structures, it's really this extensive concrete that's starting to become more critical. Okay, so all these other ones are satisfied. This is the governing one. That's the one that happens first. A little bit of extensive rebar, almost nothing for repairable damage except for maybe a 4-second period. All the other periods are lying elsewhere. And then as you go to shorter period, it's the minimal that's starting to govern. And in here you can see that there's a good cluster of half, 1, and 2 seconds. But that's your minimal side. So really, for longer periods, you're more out here. For shorter periods, you're more in the minimal damage performance criteria that governs overall. So this is for Montreal. Vancouver's Class C, you see a pretty similar trend. You see the 4 seconds and the 2 seconds are way more out here. You see a little bit of just a smidge more in the repairable region. And then again, the extensive reinforcement, there's a little bit, but as you're going towards the minimal side, again, you see some bars showing up over there. So quite similar to the trend in Montreal for Vancouver Class C. Now let's look at governing criteria when we look at all 4 seismic hazards, and these are normalized by the period. So you can see the blues, the minimal is, again, minimal reinforcement is staying more to the left, okay? When you look at the extensive, you're coming more to this side. So longer periods are governed on more occasions by extensive damage. Shorter period structures are governed more by minimal damage. And repairable, there is a very little correlation there. So it almost never governs, which means if you can target in a high-paced environment when the contractor is breathing down your neck and you have to come up with some quick designs, you can start to kind of see which one of these governs. And this is especially true when we're in a bid design scenario, where you have 3 months to do a bid design and you've got to do a good design, not overcomplicate things. You don't have time to run a lot of pushovers and time histories, but you got to come up with a design. You got to pass on some basic drawings to the contractor for them to price things out. You start to rely on some of these type of trends, and as you gain more experience, you start to learn more of these kind of tricks of the trade. But this is an academic paper, which is really, really good, and is showing, if you're running into the longer period structures, you're probably going to be in the extensive side, more on the concrete, not so much for rebar, and minimal is going to be for the shorter period structures. And what would this tell you if I were in the design office and I have to look at all 3? I probably wouldn't even look at the repair rule, right? Okay, so this is a very telling slide, and again, an indictment of the R factor method, or the force-based method. So 4 different things: 5-meter cantilever with some stiffness at the base, and then same thing for 10, the cantilevered and the fixed columns. But you see, when you run different cases for different periods, the R factor is not a straight line. It's look at the spread in the R factor, right? So it's a huge, as you're running all these different time histories, you're getting all these different R values, which means it's not a very robust way of looking at it. So I'm not saying we throw it out of the door, but I'm saying just it's got to be a little bit, you've got to pay a bit of attention to it. So Eastern versus Western. 3 different cases: 915 diameter column with 5 meters height, and a 5-foot column or 1520 diameter column with 10 feet height. 1 second period, 1 second period, and 2 second period. Axial load ratio of 5%, 5%, 10%. Class C, Class E, Class E. So these are the different parameters. 5 meters, 1 second, 5% axial load ratio, Class C. For Vancouver, minimal damage governs, okay? And my D over C, or my C over D, is 1.5. So I've got 50% reserve. The same thing for Montreal happens. My minimal damage governs. The code says you cannot put less than 0.8% rebar. So I have to put 0.8% rebar. And I have 5% extra capacity, 50% extra capacity. Here, I've got 600% extra capacity for Montreal, okay? But this is telling us, look, minimal damage governs in most cases, but you get a lot less reserve here and a lot more reserve there. What happens in this case? So this is Class E now with 1 second. It's the same thing, it's just the class has been changed. Just to meet my performance, it's sitting at 1, I need to put 2% rebar, and my governing is minimal damage on and the reinforcement. And the same thing I do here, my rebar can drop down to 0.8%, not 2%, and I still have about a 200%, 100% reserve. I'm at 2.1. Okay. The last one, Class E, 2 seconds, 3% rebar, and barely just meeting the performance. 10% reserve. The minimal damage on reinforcement is getting me there. 0.8% minimal damage. So compare this to that, and compare this to that. Okay, so you can see as I'm jumping up the classes here and the period is increasing. For Vancouver, I'm having to put more rebar. And here, my 0.8% is just getting me through everything. So just to conclude then, we have this performance-based design for more important and irregular bridges. For short to medium period range, 0.5 to 1 seconds to 1.5 seconds, it's usually the rebar strain minimal damage criterion that seems to be governing. Now, as the fundamental period increases, there are more and more cases that are jumping over to the extensive side. Okay, so you're going from one to not the other extreme, which is life safety, but you are going up 2 levels, and repairable is almost never coming into the picture. Minimal damage concrete strain doesn't seem to govern anymore, with 0.006 being fairly relaxed. Repairable damage, as I said, it governs in very, very few cases. The equivalent R factors that we used, they don't seem to correlate very well, and so you apply the same factor to all structures, and your force-based design is going to give you different damage every time because there is such a huge spread. Well, it's an explicit and rational damage criteria approach. You know what you're getting into, you can quantify it, and that's pretty much all I have. So thank you very much for joining and staying put, and hopefully you all learned a few things.
Thank you.
So just a small.
3 o'clock?
Perfect timing. Yeah.
Oh, thank you very much.
Okay.
Dr.
Maybe you can put the slide at the
Oh,
back.
sure.
The first slide.
Which one?
Like your
My first one? Yeah.
Yeah, very first one.
Okay.
I was trying to keep my eyes closed and listen.
That could be really good or really bad.
Yeah, the medication I'm taking is
Putting you in a, yeah.
Yeah.
Is that good enough?
Yeah.
Let's
So you
just,
can put in the slide. Okay. Okay. Thank you so much.
thank you very much. Thank you very much. I really appreciate it.
Yeah.
I really
Thank you so
appreciate your time, and
Yeah.
you know, it's been many hours, so thanks for staying awake and asking lots of good questions. And
Yeah.
again, if you have any questions, then
Actually, please don't forget to send them the assignments. We'll hand it over after the solve it. Right? And Dr. Adil, please.
Thank you.
Oh, we have to put your slide.
Okay.
yeah, I'll do that.
Is that on the desktop?
I have it.
Thank you. Thank you very much. Thank you. Thank you very much. Thank you. Thank you.
Let's take a group photo.
Yeah.
For the workshop, maybe we can go back to the previous one. I don't know. One thing.
This one?
No,
Your workshop
Okay.
for them. Yeah, please.
you have to close this one first.
Yeah, we have 1 minute. My meeting has just started. So I am getting late. Okay. We don't actually need the video.
Yeah, it's still running.
Shall I close it?